A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. First and foremost, I would like to say Jazakallah for everyone joining. And Assalamu alaikum wa rahmatullahi wa barakatuhu. So, welcome to our monthly AMSA science talks, AMRA science talks, I should say, hosted by Ahmadiyya Muslim Research Association, where we bring experts from different fields to give short introductory talks which are accessible to everyone, um, just for our own benefit and to broaden our knowledge as well. The program for today, as always, for those of you who perhaps have joined us for the first time, is that we're going to start off with Tilawat, and then I'll give a short introduction of our guest speaker for today. And I'll hand it over to our guest speaker to go through their main presentation for the day. And after that presentation, inshallah, we'll have a short question and answer session where the audience can use the question and answer feature or the chat feature on the call, as well as raising their hand and coming off mute to ask questions. So, without any further ado, let's begin the program with Tilawat al-Quran. Can I please request Hafiz Intisar Sahib to come off mute for Tilawat?
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم هو الله الذي لا إله إلا هو الملك القدوس السلام المؤمن المهيمن العزيز الجبار المتكبر سبحان الله عما يشركون هو الله الخالق البارئ المصور له الأسماء الحسنى يسبح له ما في السماوات والأرض وهو العزيز الحكيم. Translation. In the name of Allah, the most gracious, ever merciful. He is Allah, and there is no God beside him, the Sovereign, the Holy One, the source of peace, the bestower of security, the protector, the mighty, the subduer, the exalted. Holy is Allah, far above that which they associate with him. He is Allah, the creator, the maker, the fashioner. His are the most beautiful names. All that is in the heavens and the earth glorifies him, and he is the mighty, the wise. Jazakallah.
Jazakallah. With Tilawat done, I am now delighted to introduce our guest speaker for today, Dr. Muddassar Rashid Sahib, who is serving as a quantum hardware engineer at Universal Quantum, having completed his PhD at Southampton. And he'll be giving us a talk on perhaps stuff of science fiction for many of us, quantum mechanics and quantum computing. So I'll hand it over to Dr. Sahib for his talk. now. Jazakallah.
Alaikum wa rahmatullahi wa barakatuhu. Jazakallah, Fatin, for that introduction, and Jazakallah everyone for having me. It really is an honor and privilege to give an AMRA talk. Actually, I was thinking about when I last gave this. I did have the opportunity, and that was almost 12, 13 years ago. So it's been a long time. Let me just share my slides. Okay. Auzu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. So as I said, Jazakallah for having me for this talk. I thought a lot about what exactly to cover. And the purpose of AMRA talks, as I've been told by Chairman Saab, is really to it's a wider audience. It's not supposed to be too technical. So I know, having seen the names on the list, there are quite a few of you who are quite technically minded. So forgive me if it's very lacking in mathematical equations and everything. But the aim here really of this talk is to try and give you a taster of the key principles that are being used from quantum mechanics in computing, and why those principles give quantum computing its power and advantage in the future over conventional computing, which for the purposes of this talk and most articles you might ever read is known as classical computing. So everything that you're doing and you're using right now, a laptop or a computer, this is all classical. And the difference now, where we start to use quantum effects, they become a quantum computer. But before I go to that, let's ask the question of, well, are there limits to classical computing? I mean, we are, why go to a certain area if there's no advantage to it, or if there's no need for it? And classical computers are amazing. I mean, what we're able to do with our laptops and phones is just a small aspect of what we can do with supercomputers and the level of calculations that we're capable of. And a lot of this is based, this technological advancements actually is an observation made by Gordon Moore, that transistors, the number of transistors we were packing into our chips was doubling every year. And so this is known as Moore's law. It states that a number of transistors on a microchip will double approximately every 2 years, leading to an increased computing power and efficiency. And so now we have trillions and trillions of transistors in a chip, and we're very efficient in doing that. And you can see this graph. It's a really nice classical illustration for anyone who's in computer science, of how we've literally, every 2 years doubled our capability to do calculations per second. And it's sort of an exponential kind of graph that's just going up and up and up. But surely there must be a limit. It can't carry on going like this forever. And so it turns out, and it's just really interesting, right? Like the way all of this technological development works is that every few decades go by and we have a technology like the transistor was invented, and then we had integrated circuitry. And whenever there's a need to overcome the challenges, a new form of technology is invented that does overcome it. And so Moore's law can't go on forever. Transistors can't become smaller. And in fact, they've become so small that they're starting to reach the limits of what they can do. They're becoming almost atomic. They're like nanometers in size. At that point, the world of quantum mechanics starts to supersede, and you don't get very nice effects unless you can control those quantum effects. So the classical way of creating these transistors is not going to work. We have to find alternative ways to go and get better computing power. And so there was in 1981, Richard Feynman thinking about this problem. So for those that don't know Richard Feynman, he's one of the greatest physicists of the 21st century of ever, in fact, because of his extraordinary achievements and contributions, but the way his originality of thought was just phenomenal. And he sort of predicted that, if you want to solve problems of physics, because physics is inherently quantum mechanical, you'll need to invent a quantum machine, in his terminology, but that essentially means a quantum computer. So a computer that can handle the complicated calculations that are required to simulate or to manipulate physics at a computational level. And so why do we need quantum computers becomes a bit more apparent when we start to look into the kind of problems that classical computers will struggle to solve as they can't go higher and higher in their computational power. So you have something like quantum chemistry and material science, for example. So here you have a molecule or sets of molecules or lots of molecules interacting, those reactions. There's a lot of different degrees of freedom. In fact, the degrees of freedom just increase exponentially as the material becomes more complicated. Inherently, to describe the chemistry that's happening, you need quantum mechanics. You need the equations of quantum mechanics that talk about how the energies and different bonds and so on will change. Not so much, not just that, it's also the fact that the way we present that equation, it's very difficult to actually simulate or code that in classical computers. You can only make a very facsimile of that, but you can't really do the entire equation itself. So we're sort of approximating what might be happening. And to some extent, that's great, but it's not enough. If we want to go further, we want to discover new materials, more optimized, efficient materials. Then the other thing is, and you'll start to see why this is possible with a lot of these things, but sort of laying, the lay of the land as such as to why quantum computers might be interesting. Is machine learning, for example, training machine AI algorithms and making them I guess better in their capability to predict the future. That training needs to happen in parallel, and there is very clever architecture. NVIDIA, for example, in the news, who've invented some fantastic GPUs to achieve that. But quantum computing provides a level of parallelism that's unmatched, essentially. And so if you can harness that, it's an amazing application in AI training and data analysis. Then this has already started a long time, and now a few decades, in fact, a couple of decades. Cryptography is the art of breaking code, and everything that we have, from our banking to our computers and any kind of safe communication online, is based on these kind of RSA inscriptions that are very, very difficult, if not impossible, to break. Well, they're not impossible, but they're very difficult and challenging to break on a supercomputer. And for all purposes, you can consider them difficult problem to solve. If you have a quantum computer, let's say another country builds it, they can break the RSA code within a couple of hours. And so that is frightening. If you can imagine the consequences. But then again, quantum computing also provides an alternative. It provides you a better way to encrypt using the randomness in nature itself. And so all of a sudden, there's a danger, and this is why a lot of companies are interested in investing, because they're worried about security more than anything. If any of the countries first gets it, they will have the power to break any code. Funnily enough, the advancement of computing, breaking codes, was one of the biggest motivators, if we go back to Alan Turing and his team. And then there's other kinds of problems as well. These kind of logistics problems are very complicated. When you have lots and lots of variables, you have to search through a lot of different parameters. And so this is where computation, you need a lot of computational power.
Sorry, Muddassar Sahab, I think you're muted. What have I done?
Was I muted all the way?
No, just for the last 2 seconds.
Okay, all right, okay.
Yeah.
Okay, so all of these problems sort of set out, and I think what would be really good is if you keep this in mind. And the question we have to keep asking is, how are these quantum computers going to solve these problems? Because there wonderful theoretical devices a few decades ago, and it was a wonderful problem to be part of and working on. But we're now talking about producing products, and so we have to keep asking ourselves, how can we actually apply this to the real world? Oh, so gone. Okay. So now, yeah, that's fine. So let's look at this classical quantum kind of divide to sort of understand how do we transition from thinking classically and then thinking quantum. Now, classically, you have bits. Everything is made of bits, zeros and ones. And zeros and ones are just light switches, essentially. You know, something goes up or down. It switches on or off. And you can code that into anything, and transistors are what we use to code to essentially manipulate that. But you can code 0 and 1 into any kind of state, in essence, to do computation. Here's a very simple representation of it. You'll understand why I've used spheres in a second, but essentially it's just 2 points in space, 0 and 1. That's it. So 2 classical bits can represent only 1 of 4 at a time. So you can have 0, 0, 0, 1, 1, 0, or 1, 1. Now, quantum mechanically, we can translate this and say we're going to invent something called the quantum bit, or for short, qubit. And this also can only take 0 and 1, or both. And this both side is where it opens up like a massive universe for us. So when you carry out a measurement on this qubit as such, you will always find it to be 0 or 1. So it emulates that classical infrastructure that we're very used to. But when you prepare it, you can prepare that when you store or encode information in it. You can encode information in it that is not just 0 and 1 or 1. It's somewhere in between of both. And so that it has it can be 0 and 1 in this instance. And so we represent this actually on a sphere, because you can imagine this point here. It's actually, if this is the axis, you can represent this point as a summation of 0 and 1 and something in this state. So 2 qubits, for example, can represent all the 4 states, all the 4 representations simultaneously. You'll see this notation again and again, but it's really just a configuration. That's all you have to think it of. So 0 and 0, that's 0 and 0, that's 0 and 1, and that's 0 and 1. So now whenever I put these, they're called kets, around them, you can think that I'm now talking quantum. But when I take them away, you know I'm talking classical. This is just a differentiation for our ease, but really it's just a configuration. So now let's hone this in a bit more and see where the power is coming through. So now, once again, I have a bit, 3 bits, which have the ability to be represented as 0 and 1. Yep. So here's 1, 2, 3 bits that can be represented as 0 and 1. And now when you go through these combinations, you've got about 8 combinations, 2 to the power of 3. And so that's 8 combinations that you can have. But once again, a classical computer would process only 1 configuration at a time. You can have, trillions of transistors, and they'll all do it 1 at a time. And so you can parallelize these kind of computations, but a single set of 3 bits can only take on 1 configuration here. Now, with qubits, once again, we represent qubits with these spheres. It's not important to know right now what these angles and all these other labels mean. All we're really interested in is this 1 and 0, and the fact that this point can be anywhere on this sphere. And so now you can represent it in this way. Once again, you've got the 0, 0, which corresponds to this configuration, 0, 0, 1, etc., etc., and this carries on. Now, what you've noticed attached to this, I've put some alpha value. So this is a just some variable that we may call that tells you essentially how likely that particular state is. It's just the way we have to code in quantum computing. Everything is made up of these complex probabilities. So now, for example, if alpha 0 was 1, then it's 100% likelihood that this state, when we carry out the measurement, will be 0, 0, 0. So it'll be 0, 0, 0. And this way we present very complicated configurations, but all simultaneously at the same time. Okay. How is this possible? What allows us to do this? Once again, the thing we want to use is how do we use these concepts and principles? The question of why do these principles even exist and what does this mean about reality and all of that, I think, even though it's against my very nature to say so, but we'll have to put it to the side because it can get very confusing and we'll be here all day discussing that. The first thing I want to introduce to you is the power of interference. Now, we are all aware of this, actually. Most of people here would have studied physics to some level and would have been introduced to waves. Waves can add and subtract. So here, for example, I'll put your focus on A. You've got a wave here, and we've copied the same wave and added them together. And what you do is you get a new wave, which is twice the amplitude of the original wave that got added together. And so now, as long as they have the same frequency and amplitude, you get this kind of constructive interference, you call this. So they sort of reinforce each other. If you move the wave slightly out in time, out of phase as such, so that they are now, you can see that they're almost reflected in time of each other around the axes. And so when you add these up, this is a high, this is positive, for example, and this is negative, so they cancel. This is negative and this is positive, so they cancel. And so you get this kind of eventual result is where you actually cancel waves out completely, and you get like a flat line. And this is destructive interference. So interference is this property of waves that when waves come together, they can add and subtract. And you see this when two ripples in a water wave, for example, collide, you can get very complicated patterns, but there are patterns where waves have canceled them out and sometimes waves have reinforced them. In fact, the canceling part is really interesting because that's what your canceling headphones are essentially doing. They're taking sound waves that are coming into your headphones and they're inverting it and canceling it out. So there's a lot of power to this, and we understand how to use this. There's a key feature of this that I'd like you to sort of just remind you, but also to focus your mind towards. A wave is defined by many, everything here is defined by certain properties. And so those properties tell us what that thing is. This wave as such would be defined by an amplitude. So it tells you how much power, how high can it go up to. Its height in terms of, this could be, power, it could be field strength, whatever it is. How high would that wave go? And then it tells you the phase, i.e. where it is in time, that particular point of the wave. And then obviously the wave is also defined by something called the frequency or the wavelength. Now, this experiment is called the double slit experiment, and it's something that you would all be aware of in some sense or another, I hope. And if you're not, then it's all around you happening. Just maybe we're not cognizant of it. You have some waves, you put them through these two slits. What happens is that a diffraction from the edges of these waves, of these slits, generates more and more waves. Those waves actually interfere, and you can see a pattern emerging on the screen. When the waves are destructively interfering, i.e. they're canceling each other out, you get dark fringes. So there's no waves here. There's no wave intensity arriving there. And then if you look at where you've got these color stripes, that's where the waves arrive, where we detect some high intensity waves. And so that's an example of adding and subtracting. And this principle of interference is essentially known as superposition. So you can take multiple waves, you can add them together, and it creates a new wave. And this superpositioning of waves is something that also happens in the quantum world. Now, what happens is you take a quantum object and you fire it through the slits. And as long as the properties are correct, the experiment is being done correctly, the slit size and everything, then you get the same pattern. Lo and behold, there are positions where we see the wave, where we see the quantum object arriving, and there's areas where they just don't arrive at all, i.e. each quantum object is represented by a wave. That quantum wave, travels through these slits, interferes, and generates this pattern. It's really important to understand that this is a behavior of only waves. Particles don't do this. Objects that are localized in space and time don't behave in this way. Now, we're talking about position, but an object is defined not just by position, it can be defined by its energy levels, it can be defined by its momentum, and more generally, we may call that a state. So an atom, for example, can have an internal state that can also do this kind of behavior. It can behave like a wave. Another example of this, just to try and the more we go through examples, the more clearer it might hopefully become, is a coin flip. You flip a coin, and now there are only two states possible, right? Heads or tails. Let's assume that the coin is infinitesimally thin. So it's just heads and tails. And the moment you flip it, you don't actually know what the outcome is going to be. There's a bit of randomness to it. But there's nothing funky about it. But at the end of the day, even when you flip it, you know that any given instantaneous time, it's only 0 or 1 in terms of only heads is facing up or tails is facing up. But there's only one possibility. A quantum coin, as such, when you flip it, when you prepare it, essentially, it's in both states. It's 0 and 1. And so what we call this is that it's in a superposition of being 0 and 1. And this enables you to now take advantage of interference capabilities of a quantum object, and such that if you prepare it correctly and you do carry out the right operations, you can actually you can cancel or reinforce certain probabilities, so the outcome that you want can actually be reinforced. And we'll revisit this again, so hopefully it becomes a bit clearer. Now, the third and the final thing I want to introduce is quantum entanglement. And it's a very difficult concept. It's very abstract. It's hard to fathom in some sense, because there's nothing classically that we sort of think about. But I think all of us can appreciate the concept of inseparability. So entanglement is this unique property of an object, of two objects, that when you combine them together in a certain way, they become linked. And that link it doesn't exist in space-time. It exists in what is known as Hilbert space, but essentially it means that those two objects now, after being linked, you cannot separate. You cannot talk about one whilst talking about and not talk about the other. They are so linked that you can't distinguish in principle, between the state of one and the other. They become what is known as inseparable. And I think it's really interesting. So when I try to understand this, I sort of often personify some of these ideas, because it helps me see a mirror in human interactions. whether it is with our parents or whether that is with our spouses or our children or friends or families or society, we are so intricately linked that if you take a person out of that link, it's not possible to define them properly. What they are and what they become is all those properties within us are intricately linked with each other. In some sense, we're inseparable. At the quantum level, you can do this very controllably. You can take the polarization of light and you can entangle them so that if you take those photons as far away as you want in the universe, you measure one, the other will be in the opposite state. And you know that for certain. And it doesn't matter how you prepare it, the outcome is always the same. And so distance doesn't matter. And it seems that the very description of what that object is changes as such. In physics, we say they're correlated. This correlation is really, really important and is a really powerful tool. Because you can imagine if I take lots of qubits and I want to carry out some computation. So, this qubit represents a set of zeros and ones, and this represents a set of zeros and ones, and this and this. Now I want to carry out a computation on this. If I do something on this, I'm actually doing it on all of them because they are linked. And this distributed entanglement enables you to do some really fantastic things. You can do secure communication into space. There's essentially, these are becoming what now is the building blocks of quantum internet. But even in calculation for computation, you may entangle two of these in a way that they carry out searches very quickly, and so on and so on. So actually, it's actually one of the biggest research development is how do we use quantum entanglement to power our quantum computers, because this is such a unique feature that it's not always clear how they might be advantageous. Now, it's all very well to set up these zeros and ones, but you want to do some operations on them. And everything in our computing, for example, is based on these kind of gates, these logical operations. And from these logical operations, we carry out everything that builds up to more complex logic, essentially. So these classical computing, you have these truth tables, and they ultimately, what are known as gates, they take an input and they give you an output. And what that input and output is dependent upon these truth tables. So as a very simple example, if I have a NOT gate, I put in 0 and it gives me an output of 1. So it literally just flips the digit. So if the bit is 0, it will change it to 1. And if it's 1, it will change it to 0. And there's more complicated examples where, for example, a NOR gate, the output is, if the input is 0 and 0, so it's comparing a target and a ancillary bit, for example, then the output is 1 and everything else is 0. So it has to be 0, 0 for it to be 1. Otherwise, everything is 0. And if we want to do computation in the quantum world, we also need to invent these kind of operations. We need to map this into the quantum world. And so then we do the same thing kind of thinking, but now we have to, I guess, change our space again. So rather than just being zeros and ones, we're dealing with a sphere, a block sphere. This, by the way, is known as a block sphere, which is in 3 dimensions, but it's actually infinite number of states you can occupy here. And so it's a massive space to work with. And what do we want to do? So for example, here, I want to, let's say, put a qubit, which started at 0, into a superposition of being 0 and 1. So this is its state 1 and its state 0. And it's over here and I want to put it into a superposition, which means that I want it to not be not be one, not be anywhere else, but halfway between the two. This is the operation. So you literally would have an atomic state, for example. You would apply this gate. This could be lasers, it could be microwaves, it could be many different ways in which you might do that. And it changes the state into a superposition. This is known as a Hadamard gate. The other important gate we want is something called a CNOT gate. And this essentially creates entanglement between two objects. And it's represented by this way. It doesn't matter, but what matters is that we have these important operations that we should be able to do. And then finally, you have this kind of operation where you'll be able to flip your state completely. So this is similar to like a NOT gate, right? So if you have a qubit pointing in down, it goes up. If it's pointing in an angle, it goes in the opposite angle direction, 180-degree rotation, essentially. And these are known as Pauli XYZ matrices, but that's convention. Essentially, they're like your NOT gate. The reason there's XYZ is because we're now not dealing with a point going from 0 and 1. We're dealing with essentially a three-dimensional space. So there's XYZ degrees of freedom. You can imagine this gets very complicated. It's not, once you know the building blocks, you can put them together. Okay, so we've covered these three ideas, and the question is, what is so sorry, one second, I just realized something. What is so powerful about all of this then? What makes quantum computers more powerful? So as a summary, you have interference, the ability for algorithms to sort of interfere. So you can create algorithms that when you've got these qubits lined up and you carry out some operation, whether that's, as I said, through lasers or through microwaves, or you do some sort of weird stuff to these. Sorry, I should re-say that. It's nothing weird here. Everything is well defined and understood. You carry out certain operations or gates, but you can tailor them so that these possibilities, these pathways cancel, and you end up getting the most probable answer at the end. Then there's this option of superposition, the idea that a quantum state lives on this kind of block sphere, and you can manipulate it, and you can put them into a state which samples both 0 and 1 at the same time, and not one or the other. And so you can carry out this kind of parallel processing within just a single resource. And then the other thing, that entanglement allows you to this distributed connecting. And so you can imagine that an entire system is connected, and you have this massive state where you're sampling not just a single 0, 1, 1, 0, 0, 0, 1, 1. You're sampling that multiple times simultaneously, use of these correlation connections, essentially. And so where a classical computer might use the same number of bits, but also would require a lot of memory, quantum mechanically it handles all of that in one go. The only thing being is that the answer you get will always be a classical one, 0 or 1. And this is a really interesting point also to take away, is that quantum entanglement, when we set this up, the whole system holds more information than the parts do individually. And you can imagine then, that once again, that gives you the power that quantum computers have here. Just to convey that again, this is a really nice illustration of the quantum maze, essentially. So let's just shut this. I can't use my, okay. So you have this classical problem of trying to go through a maze, and a classical computing routine might sample all space and then find, oh, this is the best route to get there. But now when you do this quantum mechanically, it's actually simultaneously looking at all the different spaces, all the different pathways that it can take. And let's go back. All the different pathways it can take. And then gives you the most probable route to the solution. Now, what about search? So if I have a classical search, let's say I have 1 million items that I need to search through. A classical algorithm on average might take half a million steps, so 500,000 steps to find out that particular thing that I'm looking for. Yeah, this is a linear search. Of course, there are more optimum routes, but just as a point of comparison. Now, quantum mechanically, we have this called the Grover's search algorithm. It's invented in 1980 something. This search algorithm takes advantage of this entanglement. It takes advantage of superposition, but importantly, it also takes advantage of the interference capability that a quantum computer would provide. And so then the Grover's algorithm finds the item out of these 1,000 items, let's say, that are coded in essentially 1,000 steps. So there's almost a factor of 500 times increase in this case. Now you might be thinking, hold on, isn't quantum computers supposed to, be even faster than that? It sounds like it's not that fast. I mean, this is pretty fast, right? Like it's a 500 times increase. And this is where some of the myths and the facts are really important. Quantum algorithms do not guarantee you that you will get a better result than classical ones all the time. So there are some quantum algorithms actually that won't perform as good. But when you get to very large ends, so when it's more than 1,000, more than 1 million, it goes to billion or trillion, then quantum computers start to win very quickly because they can do this. They handle large numbers much more easily than classical computers can. And there are obviously other operations, other things you can do that give you even better kind of speed up and efficiency. But it's about finding the right problem. Not every problem needs a quantum computer, and not every problem is most efficient on a quantum computer. I also wanted to sort of just give you an idea of this. I wonder if this link works. Yeah, just to hone in this idea. Let me just share. Let me see if this opens up. Yeah, it loads up. Okay, I'm just going to change the screen because it doesn't allow me to do that. Sorry, bear with me. Okay, I hope you can see this. So this is the IBM computer, by the way, and you can load on and you can load your own sort of program and try things out and see what happens. Now, in this very simple example, I've set up a 2 qubits, right? This qubit is doing literally nothing. It's just a single qubit really that's at work. And you can see that we can inspect what's going on. Let's go to sphere. So remember the sphere, everything lives on this sphere. And when I apply this Hadamard gate, I essentially carry out a superposition of the states. And you can see the changes in probability as to what's happening. And if I move this to, let's say, a 5 qubit register, this was a 3 qubit register. Yeah. Let's say I have to search I want to search for a state called 101, let's say. Yeah, so this state I want. But I start out at 000. And I apply this search algorithm. Now, it's not important the why I'm doing it this way or that way. Once again, the thing that I want you to take away is that there are these operations we can do, and pictorially what's happening is that this in this abstract phase space, this abstract block space, we're just literally just moving this arrow around. And so if we go bit by bit, what we do here is we entangle, we put all these 3 qubits into a superposition, right? Then we carry out another operation, another form of superposition between just a more refined subset of those states. Then we carry out some entanglement. Then we carry out, a series of this kind of superposition and entanglement and rotation. And it's literally figuring out what of these things would do to the state. Eventually, you get to, hopefully, if things work out correctly, you get to the state you want. And it comes out with the answer. This, by the way, is just a measurement thing. So it comes out with the answer that you want, which is 101. Once I've done this simulation, I can actually send it to the IBM quantum computer and send it to run my algorithm. So this is just a search algorithm. You can do it with a 5-qubit register as well. I think that's the maximum you can do. But it's something you can play with and get to understand how some of this stuff is working. And it's like Lego. You connect these things. Once you know what this operation does, you just connect it and drag and drop the way you want. Okay, so this is an example of a quantum algorithm that we might run that's using the power of all of this, and the answer that you get at the end, you can see is high probability, approaching 79% or something, that the answer is 101. In your search that you wanted to carry out, I wanted to find out 101, a state 101, whatever it is, and it found that for me. And this can grow very, very high numbers of qubits, and it still find it for you. All right. So now that I hope you get a gist of some of the different applications, some of the power of quantum computing. How do we apply this to some of these applications? So drug discovery, for example, you have these different variations of complicated molecules that come together and have effect on your body. You want to figure out how do you do this. Current pharmaceuticals, they do carry out very complicated molecular simulations, but it's an approximation because inherently the system's quantum. And once again, you need a quantum computer to be able to carry out that full representation of those quantum molecules that we're working with. I mentioned AI training. You can see that it can deal with large numbers of items simultaneously. If you can figure out how to couple that to a training algorithm for a quantum for an AI, then you can use the power of quantum computing in AI training. Same thing goes with material science, which is inherently quantum. Cryptography we talked about earlier, but just a reminder, it's this ability to search through lots of different permutations in parallel that enables you to break things very fast. What would have taken 10,000 years for the best supercomputer takes maybe a couple of hours for the quantum computer, or a week at best. And then there's the logistics problems, which are really complicated movements of high number of variables, and essentially you code this into some sort of differential equation, and once again, quantum computer can handle multiple solutions to these differential equations. And there's also impact now talking of how energy and climate change could take advantage of these things as well. in terms of finding the better materials, of more energy efficient um, systems that we could build, and et cetera, et cetera. And the list really goes on. There's also financial markets as well, which I haven't touched upon at all. But it's not all, you know, hunky-dory. It's not all nice and beautiful. There is a lot of challenges ahead, but that in itself, I guess, is definitely beautiful, because those challenges are really amazing challenges, really captivating challenges. But you can divide the challenges that quantum computers face into two areas. There's physics challenges. So how fast are these? There's a lot of terminology here. It really doesn't, to some extent, matter. I've introduced it so that you know how to allocate what I'm saying to those terminology, because eventually, if you go into these fields down the line, or you interact with quantum computers, hopefully within the next 10 years or so, they become important for you to know. But fidelity, for example, tells you how many errors, how many tiny errors a quantum computer has. I haven't talked about, you know, the fact that you have this state, this atomic state, or this substrate that you use to create these qubits. Qubits are very, very sensitive. They're not easy to create, and then once you create them, they're not easy to hold on to. They lose that information very quickly, whatever you've encoded in them, because they're susceptible to noise, to magnetic fields, to the Earth's magnetic field. There's lorries going by, create vibrations that can change the thing that you're trapping, that you're holding, and that can change everything. You lose information. And so they have to be, you know, there's a measure of how good your qubit is. How long can you keep that information in that qubit, which is known as coherence time. Then there's gate speed. How fast can you actually carry out these Hadamard or these C0 gates? Because if it's all very well that you can code and do this parallelization, but if it's going to take you, you know, a minute to do a single gate, where transistors flip at, you know, nanosecond speeds, then forget it. You're never going to beat a supercomputer. It's just not worth it. So how fast can you do this? Currently, it's milliseconds to nanosecond is achievable, and depending on which qubit you're using. But it's very difficult to the challenge of physics is to try and improve this, essentially. And then scalability. Can you get how do you get multiple qubits that might be separated in space talking to each other, because that's where the power comes in? How do you make sure that once they've talked, that link is not destroyed? And this is really, really challenging. Like, it's a really difficult problem that is being worked on. We'll move on. So engineering, and then the second one, as I said, is engineering, because in this example, inside here is where the qubit might live. And all of this else is infrastructure that's required to communicate to it, to control it. And we end up occupying rooms, you know, to just talk to this tiny little area of space where a few qubits might be there. This isn't, so you've got to figure out how to compress all of those electronics and systems into a single thing. I mentioned that you have a qubit, for example, you might put information into it and it loses information. So to get around that, you have error correction. So you have same qubit and you code the same information in, say, up to 8 or 10 qubits as well. So now you have a lot of overhead, essentially, to carry out, to have one logical qubit, you have 10 or 8 physical qubits for redundancy, essentially, because you lose information. This is a problem, and how can we resolve that? There's control systems I've already talked about. The other interesting problem, and there's a lot of work now being done on it, is skilled labor. Not everyone understands these concepts. You're not taught this from an early age. It's often a barrier because people think that it's too hard. I mean, it's not. It's just another kind of language that you have to learn. I have to say that I work alongside software and mechanical engineers and electronics engineers, and you know, the their way of understanding the problems is amazing. And it's not like you need a physics degree to understand these ideas and to manipulate and use them, but the skilled labor doesn't exist, and there's a massive shortage of it. So those youngsters were thinking the future's bright, as you'll start to see in a second as well, when we talk about money. Yeah, this is the other really important part actually is we actually don't know how to apply this. I've talked about possibilities, right? And there are a few examples like this Grover's algorithm of how you search through an unsorted items in quantum computing, but we don't really know how yet to take all of this and put it into a real world problem. Those real world problems have to be coded in a very specific way for quantum computers to try and solve them. And so that transition also is not quite clear, and is an active area of research. But there are obviously a lot of ideas in there, and I'm sure we'll solve that. Okay, we'll go past this. I'm conscious of time. I wanted to also just mention a few things. There's lots of ways of creating quantum computer. The main important ones that you might come across is photonic based. So these are light based. You have these substrates made out of often lithium niobate or the silicon substrates where you encode light into these waveguides essentially. And then you use light itself, the properties of light, because light, when you talk about at a single particle level, light becomes very quantum mechanical. It can act, the internal states of it can be encoded with information. And so we can encode all of that and use it onto a chipset, and that's what some companies are working on. There's also atomic based. It's very easy to hold millions of atoms in an electric field or in a laser trap, and we do this relatively often in all around the world, in labs around the world, physics labs around the world. And so once you can do that, you can have individual atoms as qubits, and you can address them. And so this is what various people are working on. And then you can also have near neighbor communication, so entanglement between nearest neighbors, and so on and so on. The other one is superconducting qubits. This is what IBM and Google are working a lot on, and they've bet their bet basically on this. This essentially is an electrical circuit using specific semiconductor wires and so on, all edged onto a chip. But all of this needs to be cooled to really, really low temperatures for the superconductivity feature to appear. And then there's ion trapping, which is what I'm working on in Universal Quantum. And here we have these kind of chips. And on top of that, on top of these chips are, we levitate using fields, atomic ions, essentially. And you can move these atomic ions around. And so you have this kind of white light, the white objects, which represent the qubits. They get moved around on this surface, essentially. But you need a massive amount of infrastructure to communicate, to control all of this. This is an example of a lab. This is the IBM lab. So, you know, it's not even clear from this picture, but over here on the left-hand side, there is enormous amounts of electronics. There's electronics here, there's electronics on the other side that might be noisy, so they want to keep it away. These pipes are going all the way to another room, which carry out massive canisters of liquid helium to pump the temperature inside this to sub nanokelvins. And then, sorry, millikelvin. And then you have these inside here, you have these additional wires and so on. And just this tiny part over here is where the chip is. So all of this to control this tiny chip. This is the zoo of the quantum computing world. There's a lot of startups, but I'm sure you can see the names of some very famous companies as well, like Intel, AWS, Microsoft. There's Continuum, which has been in the news recently, INQ as well, and UQ, so Universal Quantum, who I work for. So there's big players and there's a lot of startups, and you can see they try to address the different aspects of it. So there's quantum processing units. So these are hardware stuff. There's specialized hardwares like lasers, like microwave detectors, etc., which are these companies making. They don't make quantum computers. They make those kind of electronics that's required for it, the vacuum chambers that's required for it. These guys take that supply, make the hardware itself that does the quantum computing aspect, and then you've got another layer of this, which is software. And the software, how do you communicate to a quantum computer? Can you use Python? No, you can't. You have to change the logic that you use, because conventional logic doesn't work in this way. So how do you translate that? It's a hard problem. So there's various companies doing that. Some companies like AWS, for example, they do it in-house. We also do it in-house. There's other companies, the bigger ones can do it in-house. It's a lot of work, essentially. And then there's applications dealing with other providers like JP Morgan, or AstraZeneca, which is a pharmaceutical company, military, cars, BMW, Airbus, whatever problem they have, how can we make a product over here that solves their problem? Because you don't want to make a product in isolation. And so you have all these buyers essentially currently. Now, I want to just show you the development of this. In 1998 to 2000, we had about up to maybe a few qubits, a handful of qubits. And this has gradually grown, it talks about different companies creating qubits. And this is a nice map, and you might see it in the papers and the news, but they don't tell you the full story. They don't tell you the fact that how good are these qubits? Do they last for like 1 second? Or do they last for like a day? You can make a lot of qubits, but how good are they? And the aim of all these companies is ultimately try and get into the million qubit range, to build hardware that can handle 1 million qubits, because scalability is a major issue, not just in number of qubits, but also the hardware that you're using. You have to condense it down. It's a big challenge, and there's a lot of promises. There's a lot of money. This is 2022. Actually, I know this is probably increased. It's, I think, tripled now, the global effort towards this. You see the big players. There's United Kingdom, 1.3 billion. There's the US, 1.2 billion. The UK, by the way, sits very strongly. We've had a very strong program in quantum computing and information in terms of research groups. And so, in some sense, a lot of the world leaders are coming out of here, out of the UK and out of, I would say, Germany and Austria, and France as well. And then there's China, $15 billion dollars. And this is an illustration of the importance attached to this. It's nothing like AI right now, but it's still a massive chunk of money, especially for physicists to be working on this. So you don't want physicists working on this. You want engineers working on this. Yeah, we can go around this. We can come back to it if people are interested. I also thought it's really hard to take all of this in one go, especially if it's the first time you're being introduced to it. So there's an amazing set of resources. I recommend. There's some amazing videos. There's a video by 3 Blue, 1 Brown. I think that's what they're called as a channel. IBM Quantum Learning, fantastic resource. And then there's also this sort of more reading-based kind of introduction to quantum computing as well. Sort of gently takes you through every aspect of it. I really recommend trying IBM. It's a really nice way to get your hands dirty without being overwhelmed. Okay, finally, I'll end with the statement by Richard Feynman that nature is classical, and if you want to make a simulation of nature, we better make it quantum mechanical. And yeah, it is a beautiful problem, but it is a hard problem. Jazakallah for listening. I hope it was informative.